Dr. Sugiyama for introduction. Good afternoon, everyone. I'm Sugimori from Hokkaido University. Today, I'd like to introduce our research. In particular, we'll focus on explaining the analytical method we use for analyzing surgical instruments. First, I'm going to explain the detection of surgical instrument tips, then touch upon the method of identifying the left and right surgical instrument. After that, I'm going to discuss the trajectory analysis of surgical instruments, especially indicators such as Jack index. Finally, I'm going to present the result of comparative analysis between expert surgeon and novice using this method. First, let's compare two important image recognition technologies, key point detection and object detection. The video shows an example of simultaneous execution of object detection with blue bounding box and the key point detection of major human joint. Key point detection is a technology that detects specific points with high precision. Representative CNN model include open pores and HRNet. The main application areas include human joint detection for pose estimation and facial landmark detection. On the other hand, object detection is a technology that simultaneously detects the position and class of object. Famous CNN model include YOLO. The main application area include the simultaneous detection of multiple objects and real-time object recognition. Understanding the difference in characteristic and application area of these two technologies is important for selecting the appropriate method in our research. Based on the characteristic of key point detection and object detection explained in the previous slide, I'm going to now explain why we choose object detection for surgical instrument tips detection in our research. Key point detection specializes in detecting specific points, and its strength lies particularly in the ability to consider relationship between multiple key points. On the other hand, object detection detects the bounding box that enclose entire object and simultaneously identify the type of position of object. It is suitable for detecting single object or multiple unrelated object. The main reason we adopt object detection is that this method can effectively capture the single important point and the surgical structure tip. Since there is no need to consider relationship between multiple points for the instrument tip, object detection is optimal. Also, computational efficiency is important in real-time surgical environments, and the object detection excels in the aspect as well. Considering these advantages comprehensively, we decide to adopt object detection for surgical instrument tips detection in our research. Here, I'm going to explain the identification of a left and right surgical instruments using a video of vascular anastomosis practice. First, for data preparation, we convert the surgery video to JPEG files. Next, we perform annotation. Here, we clearly define the bounding box setting center of the instrument tip in each image and whether it is left-hand or right-hand instruments. The major advantage of this training data creation method is that it allows detection of left and right instruments separately. This makes it possible to extract the movements of the surgeon's left and right hand individually with a single object detector. This slide shows the learning result of a surgical instrument of tip detection with added left and right information. The light blue bounding box in the image indicates the right-hand instruments, while the blue bounding box indicates the left-hand instruments. This result shows that this method can accurately identify left and right instruments. This technology enables individual tracking and analysis of the movements of both hands of the surgeon. Next, we will address the question of how to objectively evaluate the surgical movements of expert and novice using video of vascular anastomosis practice. The right side shows a video of experts, while the left side shows video novices. By analyzing these videos, we examine whether we could quantitatively evaluate the differences in surgical skill between the two groups. The novice group consists of young neurosurgeons, mainly first to third-year residents. Their characteristic is that they have no experience in extracranial, intracranial bypass surgery. On the other hand, the expert group consists of neurosurgery specialists with extensive experience. I'll briefly explain the analysis method for evaluating the trajectory of surgical instruments. Our analysis method begins with creating an object detection model to detect left and right instruments. Using this model, we obtain time series coordinate information of the instrument tip from the surgery video converted to JPEG. Next, we perform the calibration using the blood vessel diameter in the image as the reference to the calculated actual distances. Then, as shown in the figure on the right side, we divide the surgery into phases from holding the knee to cutting the thread, and analyze the movement of the instruments in each phase. Especially, we calculate the normalized jack index from the time series coordinates, movement distance, and the time taken. Finally, by comparing the elapsed time for each phase, total movement distance of the instruments, and the jack index, we objectively evaluate the differences in surgical skills between expert and novice. Jack index is a very important indicator in analyzing the movements of objects. It represents the third derivative of position with respect to time. That is the rate of change of acceleration. Physically, it serves as an indicator of the smoothness of movement. In our research, we use a normalized jack index, which is a further development of this concept. The interpretation of this index intuitive. A low jack index indicates smooth movements, while a high jack index indicates unstable and jerky movement. And in other words, we predict that the movements of skilled surgeon will show low jack indices, while those of novice will tend to show high jack indices. This is an example of analysis using trajectory analysis software. This software analyzes the movement of surgical instruments for multiple angles. This main function includes displaying the coordinate change of instrument tip and the three-dimensional trajectory over time, and outputting indicators. This allows for object evaluation of the characteristic and the efficiency of the surgeon's techniques. This slide shows specific results obtained from the trajectory analysis of surgical instruments. The graph compares the expert and the novices. First, looking at the elapsed time, and we can see the overall expert on the left side of the graph complete each phase in the shorter time. Looking at the graph of the normalized jack index, we can see that experts generally show lower jack indices, and which means their movements are smoother. This result objectively demonstrates that the experts perform surgery with efficient and smooth movements. Such analysis can potentially contribute to improving surgical techniques and developing effective training programs. This slide shows the contribution each indicator in each phase of the surgery. It visualizes how the three indicators, time, total distance, and normalized jack index, contribute to the 4 phases from phase A to phase D. From the analysis, we can see that while the procedure time indicated by the green is naturally makes a large contribution, and JAK index indicated by the red line and the dot red line also makes a similarly large contribution. This analysis results show the characteristic of novices. The trajectory is irregular, the coordination between left and right instrument is low, and the JAK index is high. This suggests that novice movements are unstable and insufficient, which can be used for feedback and improving training. This slide shows the analysis result of expert compared to the analysis result of novice. The trajectory is smooth with less waste, and the movements of left and right instruments are coordinated. The JAK index is low, and these results indicate that the movement of expert are stable and efficient. Finally, I'll explain the prospects for surgical instruments detection and motion analysis using AI. AI is useful for high precision instruments detection, object evaluation, advanced training, and safe assessment. There are many techniques, challenges, including learning with original high-quality images, realizing real-time processing, improving accuracy, and ensuring versatility. Implementation is clinical setting and many other issues. In the future, we expect to see the reduced surgery time and the risk, optimization of a personalized surgical plan, and the effective training of a next-generation surgeon. What I've talked about today is how we utilize the result obtained from the trajectories of surgical instruments, but we believe that by applying these efforts, AI-based surgical support system will evolve. And this concludes my presentation. Thank you for your attention.